In this video, we're going to define what the dot product of two vectors is. We're going to introduce that through mechanics. So imagine you have a body moving from point A to point B, and you apply a force to that body. So if your force has the same direction as your displacement, your motion, it will help the motion and so bring energy to it. So along the displacement from A to B, the total amount of energy it will bring is just the product F times AB. Now if your force has the opposite direction, then it will take energy from the motion, and the total amount of energy it will take away is minus F times AB. If your force is perpendicular to the motion, then it will neither bring energy to the motion nor take energy from it. That is what we call the work of a force, the total amount of energy a force brings to or take away from a motion. And to calculate it, we introduce that new mathematical object, which is the dot product of two vectors. So we call it dot product because if I read it, I read vector F dot vector AB. We can call it also scalar product because the result of that product is just a number, and scalar is a posh word to say number. So what we've seen thus far is that if vector F and vector AB have opposite directions, then the scalar product is minus F times AB. If they have the same direction, then it's plus F times AB, and if they have perpendicular directions, then it's just 0. What if now the directions of vector F and vector AB are not the same, not opposite, and not perpendicular? So, for example, we have those two situations, vector F1 and vector F2. So we can use a square grid and resolve vector F1 as the sum of the horizontal red vector here and the vertical red vector here. Likewise for vector F2. As we said before, the vertical vectors can be dismissed completely. They will not bring energy to the motion, they will not take away energy from the motion. So we just have to consider the horizontal components. So to be more precise, I've labeled my horizontal component W. I can see that W has the same direction as vector AB, so my scalar product will just be W times AB. So the magnitude of W is what I want to calculate now. As I said before, what is important here is that my grid is square, right? So I can use trigonometry to calculate the magnitude of W, and W is just F1 times cosine of alpha, where alpha is that angle here between AB and F1. So finally, vector F1 scalar vector AB is F1 times AB times cosine alpha. I can do the same thing for F2, and I get vector F2 scalar vector AB is just F2, the magnitude of F2, times the length of AB times cosine beta, where beta is that angle over there. Alright? So we said before that the scalar product F1 dot AB had to be positive. Well, it works because alpha is smaller than pi over 2. It's acute, so its cosine is positive. What happens for beta here is that beta is bigger than pi over 2, so its cosine is negative. So that is why here, even though we do not see a minus in that product, well, the result of the scalar product vector F2 times vector AB is negative because cosine beta is negative. So that's our definition. If we take two non-zero vectors u and v, vector u dot vector v is the magnitude of u times the magnitude of v times cosine alpha, where alpha is the measure of the angle between u and v. Well, you can notice that I can write it the other way around. I can write v dot u. It will not change here, that product, magnitude of v times magnitude of u, and it will change my angle. I will get minus alpha, but since cosine is an even function, cosine of minus alpha is equal to cosine of plus alpha, so it doesn't matter actually. So now if I have two vectors a and b and they do not share the same starting point, the same origin, well, I just have to draw them from a common starting point, right? So I get vector a dot vector b is equal to vector kl dot vector km, and it works. If I don't want to use cosine and the trigonometry, what we noticed before was that the only component which was important here was the horizontal one. So how do I get the horizontal component of vector AC? I just need to drop my point C on the line AB and I get H. H is called the projection of C perpendicularly on AB, right? So if vector AH and vector AB have the same direction, as happens here on this side, then the scalar product is just plus AH times AB. If AH and AB do not have the same direction, well, it's actually what happens on the other side, so it's rather vector AD times vector AB. Then I get a product which is negative, so it's minus AH dash times AB. So that's it for now.